In this lesson, we'll talk about the natural logarithm. Since we just talked about exponential functions, the natural logarithm comes up very easily in the process of solving some of these equations. If t is in years since 2000, the population of Nevada in millions can be modeled by this function. That's an exponential function. We want to know when the population will reach 4 million. But in order to solve that equation, we actually need a way to undo an exponential function. To do that, we're going to use the natural logarithm. So the natural logarithm of x, it's usually written ln of x. The ln is a switched version of natural log because it came from a language where the adjective comes after the noun. Officially defined, this is the power of e that we need to get x. So in other words, if we have that the natural log of x is equal to some c, c is the power of e needed to get x. So e to the c would equal x. This also means that you cannot find a value for natural log of x if x is less than or equal to 0. A few properties come out of the natural logarithms. You have the log of a product can be written as the sum of the logs. The log of a quotient can be written as the difference of the logs. One of the very practical ways we're going to use it is the log of something raised to a power can have that power brought to the front and just have that times the natural log of a. The natural log and the e cancel each other. So the natural log of e to the x would just be x, and e to the natural log of x would also be x. That's because these are really inverse functions. As far as we're concerned, this is the full set of the properties of logarithms. So if you think you have another property, it's not going to be a correct property. Don't make up rules. For this class, these are the only logarithms we're going to consider. We won't consider any logarithms of different bases other than just this natural logarithm. Here's the graph of the natural log of x. The natural log of x always has 1 as its x-intercept, and that's true for any log. And it's an increasing concave down function that goes towards negative infinity as x goes towards 0 from the right. Remember, this function is not defined at x equals 0 or x equals a negative number. Let's use these properties to solve an easy equation. Let's find t when we have 4 to the t is equal to 12. Anytime you have an exponent that's a variable and you want to try to get to that variable, you need to use a logarithm. So the first thing that I'm going to do is take the natural log of both sides of this equation. Now, what was the point of doing this? The reason is that a natural log has the ability to take something in the exponent and bring it to the front. This gives us t times the natural log of 4 is equal to the natural log of 12. And now it's just a simple division problem. If I divide both sides by the natural log of 4, this is going to get t by itself. I get t is equal to the natural log of 12 divided by the natural log of 4, which, by the way, this does not have anything to do with the natural log of 3 or any other sort of simplification you could make here. However, I will approximate this to about 1.79. Which makes sense if you think about it. 4 to the 1 would be 4, 4 to the 2 would be 16, and given that 12 is closer to 16 than 4, it makes sense that this number is a little bit closer to 2 than 1. Now let's solve the equation that we motivated this section with. Let's determine what year the population of Nevada would be projected to reach 4 million. We are going to use a logarithm, but first we need to get the exponential expression by itself. The first thing we'll do is divide both sides by this coefficient that's in the way of what we're doing at the moment. On the left side, I'll leave it alone. And on the right side, I'm just left with my exponential expression. I don't want to change anything or try to approximate around mid-problem, because this might mess up my accuracy at the end. Now that we have the exponential expression by itself, we're going to take the natural log of both sides. With this log in place, we can bring our t to the front. Now, just like in the last example, we can now divide by the number accompanying the t. This gives us this rather complicated expression. So we've got the natural log of 4 divided by 2.02, which I again did not round, because I didn't want to lose accuracy, divided by the natural log of 1.036. If we put this in a calculator, we get approximately 19.32, and this would be in years. Now the question was asking us, what year would the population be expected to reach 4 million? Sometimes this is a little bit confusing because you're looking at a year versus a number of years. This is why I was very specific when I said t is the number of years after January 1st, 2000. What this would mean is you actually would always have rounded down, because from January 1st, even if it were 19.99 years, you would still only be 19 years in the future according to the calendar. With that said, I'm going to round this down to 19 years. And again, I'm rounding down regardless of whether my rounding rules would say to do so. In general, if you're not sure, round down. With that said, 2019 was the year that the population would have been projected to be 4 million. This would be an interesting fact to look up, because at the time of this recording, this is way past 2019. Let's solve one more equation using these methods. Just like last time, I want to start off by dividing away this coefficient that's in the way. This gives me 9 to the 4th is equal to e to the 2t. And just like last time, I'm going to take the natural log of both sides. But something interesting happens here. Now normally I would just take the 2t and bring it to the front. But when you're dealing with an e, this is the other property. The natural log and the e actually can cancel out and just leaves behind the exponent. So after this cancellation, all we have left is the 2t. So then let's divide both sides by 2, and we get a value for t of the natural log of 9 over 4, which again I didn't round, all divided by 2. And just to give a decent approximation, this is about 0.406 as a final answer. Keep in mind though, these exact answers are also useful.